Alright, today we're going to talk about the cascaded dynamic notch improvements made in Betaflight 4.0. But before we get started, big thanks to Ken Mitchell, Chris Thompson, and George Hartman for all their work to think this stuff up, get it coded up, and get it put into a pull request. Also, thanks to the other devs that do the great peer review and get the code cleaned up even further and optimized. Mike Keller, AJ, eTracer or Bruce, MacGyver Jim, and everybody else in the Betaflight Slack dynamic filter channel. So before we get into the details, if you have not watched the filtering fundamentals video, I will make a link to that in the upper right. Go ahead and click on that and make sure you watch that if you're not, fully versed or well versed, at least a little bit, on attenuation and frequency and just the details of what the heck we're talking about when I say things like attenuation, phase delay, noise, and frequency. If you don't really know, have a good grasp on those, do check out that video first. So pause it here, go check out that, and come on back.
One eternity later.
Alright, so we're going to use the filter calc tool, which I'll have a link in the video description. I'll try to make a link in the upper right. I don't know if I can do that or not. But go ahead and download that if you're looking at the details. Honestly, I'm just going to use it here for just picture representation, just to kind of show you what the heck is the dual or cascaded dynamic notch to begin with. What we normally have for the classic dynamic notch in Betaflight is a single notch filter. And this is an attenuation graph where it shows noise attenuation along the frequency spectrum. So motion is down here, sub 100 hertz, 50 hertz is prop wash, everything just rolls left and right is down here at 1 to 5 hertz. And everything up here is high frequency motor noise we want to crush. This shows the attenuation of crushing that noise. So any noise, just showed in the filter fundamental, any noise at, like, for example, 350 hertz right here will be reduced to 0 right at the center of the dynamic notch. It will be reduced to half if there's sideline noise at 300 hertz. And then this obviously does the dynamic notch. What it does is it moves up and down based on tracking of where the motor peak noise is, so it can ideally crush it to 0 all the time, but it can't perfectly track where the noise is, so some kind of leaks through on either side a little bit. And that was recognized that, hey, the notch is very precise, but it's always behind a little bit. Takes a little bit for it to do its calculations and things of that nature and follow the peak motor noise, so we get noise kind of leaking through on either side. So how can we make that better? Well, a way to make that better is to have two notches that follow the FFT, which is the motor peak center, and what's the calculation that's used to determine the motor peak is called the FFT. So you're going to see that a lot. People will say, what's your FFT max? FFT, that basically means, once it's looking at the vibrations, does the calculations, the fast Fourier transform, that's really determining where the peak is for those motor vibrations, and it's tracking that. So it's our max FFT here, right here is the motor peak. So instead of having one notch exactly on top of it, we're going to have two kind of on either side, and you can adjust that width for how far they're away from the motor peak by this factor right here. So why go this route to begin with? Well, if you can look here, a lot of times when you had motor noise, either you had one low pass filter or two low pass filters on the gyro, and you can just see the difference. This is the phase delay for a low pass, the second low pass filter. Same phase delay by both notches added together is 0.7. This is low pass filter, and you can see that the low pass filters up here, you just get more attenuation with notch filters than you do with low pass filters. That changes as you get up into this spectrum up here, but right on top of them, those noise peak, notch filters are just specifically designed to handle peak noise, so they're really good at crushing it. So it's just more effective. So what's nice about this sheet is you can go ahead and download this, and this is the V8 version. You'll see at the link, and this is completely set up to show you how things are working with the dynamic notch and low pass filters if you're interested in that. What I'm going to do next is kind of go through the variables, and then you're going to really give a brief on. It's really quite simple. You have to set one CLI variable to get 90% of the way there for a good filter setup with this regime. And the bonus is you don't even need a black box log. You can do it through a new OSD element, that's the FFT, in your stats when you go ahead and disarm. So let's get into it. To cut to the chase, for the folks that aren't interested in all the gritty little details, which we will cover in this video, I'm going to go ahead and flash up to the latest version of Betaflight now, and then we'll talk about all the details in a little bit. But before we want to do that, we do want to make sure before we flash up, we do a diff all to get all our little settings so we can paste those in to our new Betaflight flash. So we'll type in diff all into the version or the firmware version we have on our flight controller right now. And what's nice about a diff all is if you have multiple rate profiles or PID profiles set up, you will get all those settings. So we're going to go ahead and copy that, and we're going to put that into a text document. So after we have a little notepad file opened, and you can see I name it diff all and have it on my desktop here, I'm going to paste that copied text into there. And you do want to go in here and take out a couple little things. Honestly, all this content at the top is not needed. Typically, you want to go into your acceleration calibration, and I usually take that out, and anything that has the dynamic settings in it here as well. So you can take out the dynamic. You can see I adjusted the notch range to low for this specific flash. I was doing some testing of some stuff, so you can go ahead and take that. You can click find, type in DYN, and really just any of the stuff that has the dynamic in it you probably want to take out, because you really do want the defaults for this. Now in this specific one I have a debug mode set to dynamic LPF. I am going to leave that because you'll see that's what we're going to want there in a little bit. You can leave all the OSD settings, all your failsafe settings. If you do your PID settings, leave all that. I would just say anything that's filter related, like if you have low pass adjustments, I don't have any here, but if you have any gyro low pass, D-term low pass stuff, go ahead and remove that out of here. We want to have the default filtering from the new release and not carry over any old stuff. But all the other stuff, your feed forward, your PIDs, your rates, that's all good stuff. All your OSD elements, that's great stuff because that's a real pain to set up. And yeah, we're good to go. So you can see here I don't have all that much stuff. Obviously the auxiliary switches and the ranges, so I do want all that. All right, so we got that cleaned up a little bit. Just make sure to go through there. Hopefully it's somewhat intuitive. If you do have questions, do hit me up. I'd be more than happy to help. Okay, so after we have that flashed up, we're going to go ahead and hit disconnect here. We're going to go down to the firmware flasher. We're going to hit on enable expert mode because you are now an expert. Hit development, pick your board, and then go ahead and pick build number 1322. Load firmware and flash the board. Once you're all flashed over, go ahead and hit connect. Now we are going to want to do this a couple times. Hit reset settings, and I'm serious about this. I don't care if you hit erase all, always hit reset settings. There's so many people I help out with stuff that after they flash up, they didn't do this, and they did hit erase all, and nevertheless they go and do this, paste their diff back in, and everything's fine then. So they have like weird behavior and then all set reset settings. So I'm weird. I do it 2 or 3 times. Do that, put your quadcopter flat on the table, hit calibrate accelerometer, then we're going to go to the CLI, we're going to open up our text file, copy all the settings, paste those in, and hit enter. After it's set everything up, type save, come back in. You may want to hit calibrate accelerometer here again if you forgot to take it out, just to make sure everything's flat there. You do want to ultimately then check your orientation to make sure that's working appropriately as well, just to make sure board orientation's all good. If it's not, go ahead and get that fixed up. I do then usually kind of breeze through the tabs and generally will look and say, okay, yeah, is that everything I want it to be? Is that how I normally have it set up? Specifically the fail-safe, do make sure you do your fail-safe checks and everything's working there before you go fly it. Now going into the PID tuning tab, we're going to go into the filter settings, and we do want to make sure that this is what we see for filter settings. So it's 150, 150, biquad, biquad, and then the stage 2 gyro is off. If this is not the settings, go ahead and put these in right now. But it is important to recognize that everything in this build is set to be dynamic. So you have dynamic low pass filter on the gyro, dynamic low pass filter on the D-term this low pass 2 on the D term is static, so it is following this. And the dynamic ones, though, are not following these 150 hertz settings here right now. Nevertheless, I want to make sure that that is set to 150, 150, biquad, bifod, and 150 here as well. What we want to do now is go into the CLI, type in get dyn, and then you can see all the variables here. And the one variable we want to set is this variable. So this variable is essentially the max peak motor noise or vibration for your quad. 150s for a 5-inch quad is probably right. If it's a micro, a 3-inch quad, it is not 150. It's going to be like 700 something. Same thing for a whoop. If it's a 6-inch or 8-inch quad, this is probably down to like 300 something. I'm not exactly sure. So how do we get this number? Because this has an impact on the dynamic behavior of these filters, which we're going to talk about here in a second, but just for the simplistic part, not everybody wants to know all those little details. So you just want to know the nuts and bolts. How do we get this number? So what we can do, we don't need to do a black box log. There's a new OSD element, and if you type in get OSD, and you can see it down here at the bottom, OSD stats max FFT. We're going to go ahead and change that to be on. So go ahead and hit copy on that, hit set, paste that in, on, enter, save, and done. I did want to jump in here with something that I forgot. If you are running a micro quad, so anything like a 4-inch or 3-inch, anything below, I would say like a 3 or 4-inch, you do need to go ahead and set this max to above 610. So maybe set it at like 615. And the reason is that we need the dynamic notch to be able to go into high range, which we'll talk about here in a second. But if you don't do that now before you do this flight to get your FFT from the OSD element, it will give you an artificial reading because the dynamic notch won't be able to go high. Essentially, smaller builds, the smaller the build, the higher the motor frequency is. The larger the build, the lower the frequency is. I think you should be fine if you have like a 6-inch, 7-inch to just leave it at the default of 450. Now, what will happen is you want to go out, do a flight. A nice hard flight on your quad. If you have to be brief about it, just go out and give it full throttle for half a second to a second or something. Depends how much space you have. But we want to try to get it full throttle or full flight. And then when you disarm the quad, you will see an OSD readout with your max FFT. So after you're done your flight where you've made sure to hit 100% throttle and you disarm, you will see this OSD stat, your peak FFT, which is basically means your peak motor noise in your stats on the disarm, since we enabled that in the OSD. And you can see here this is for a Mobula 7, and this varies. If you have a Mobula 7, sometimes it's 750, sometimes it's 8, depends if this was just a quick flight. But this is 823, so you can kind of round it off. 825, it's 800, 810, somewhere around that number. Essentially, we're going to go back into Betaflight with that. We're going to type in get dyn. We're going to change this to be that number plus 25 hertz. So let's just use an example that for a 5-inch here, that it was my max FFT was 485. So we're going to go type in set FFT 510 because we added 25 hertz to that. Save, and we are done. When you fly this, your dynamic low pass filter, your low pass 1, will move from 150 hertz from around 20 to 25% throttle up to 510 hertz. The dynamic notch will have a width of 8, and it will get wider as it goes up in hertz, and the width will get wider to tackle noise more effectively. That's why we can move this low pass up to reduce latency. And then your D-term low pass filter, D-term 1, will move from 150 hertz up to 250 hertz as throttle increases. So give it a fly, see how you like it. If you want to make some tweaks, stick around. We're going to go into more of the details. All right, as we just talked about, the settings in your graphical user interface for now, or the configurator, are not what you're going to be looking for when it really comes to low pass 1 for either the gyro or the D term. It's really these two top numbers. It is not following those. It's important to recognize that almost all the stuff, improvements in Betaflight, you can always change it back or roll it back by changing some settings to like a previous release. So, say for example, you just don't want those low pass filters to be dynamic for some reason. You go ahead and set your gyro, your dynamic LPF gyro min, set this to 0. Same thing for the dynamic LPF min hertz for the D term, set this to 0. Then the configurator values that you see in the graphical user interface will be valid. So the 120, or you can set these by default. They're still at 150 by quad, so on and so forth. So you can set those to be whatever you want, and you don't have dynamic low passes at that point. I don't recommend that, but it is an option. So let's talk about some of the dynamic notch settings. So you'll notice in here a few changes that have been made even from 4.0 code that the stable release isn't even released yet. We're using a Q factor and then a percent width. Now we kind of touched on the percent width. It's pretty straightforward. It takes the center range, and you can kind of see it here wherever the FFT is in the center, and it multiplies that 8 by 8%, so 500 by 8%, so on and so forth. You can use the Excel spreadsheet to kind of look at the math that's going on and how it's working. But as the notch goes up in hertz, it gets wider. Also, the gap, the breadth between the two center points gets wider as well. So you can kind of see that position, that hump in the middle here where attenuation is a little less, kind of stays the same. It just gets wider to handle a wider breadth of noise, and that's what we want. Also, latency goes down because the notch is up higher in frequency. So the default is 120. I have seen people moving this up to 220, so on and so forth. The latency drops honestly a decent amount as you go up. If you don't want two dynamic notches, if you don't want cascading, you just want a single, you would just change the width to 0, and that will give you a single notch, just like the Excel spreadsheet shows. So you can use that as a guide to kind of see what the heck's going on. And you can see here that 1.2 or 120 corresponds to a 210 notch width. If you're used to the old, where we had a cutoff for a notch, so on and so forth, at around 250 hertz, and 580 when the notch center is at 500 hertz. So you can see just the single notch gets a lot wider with a fixed Q. So why was it switched to that? Well, in the past we were kind of artificially adjusting the width when you don't really need to go to that extent. The Q, just having a fixed Q, which is literally what is in the equation for the filter attenuation, you just have that fixed Q and it naturally gets wider all by itself. So it was a good way to simplify it. Same thing down here. You can see, just for example, an 8% means at 150 when the center is at 150, so it's 8 times 150, 12 hertz, and that's 24 because it's offset on either side of the FFT center. 0 provides for a single notch. Higher percentage is a wider gap. Oh, and I did forget one thing. The dynamic notch min hertz at 150, what that does is it doesn't let the dynamic notch go below whatever that hertz value you have set at there. So if you want to have kind of more aggressive or less delay at lower throttle ranges, you could set that to, it's going to follow the peak. So if your peak, if you have a strong peak that doesn't really go below 250, it's not going to go below 250. But if you want to make absolutely sure it doesn't go below 230, 250, whatever the number is you want, you can go ahead and adjust that. That's what that is. Okay, so we already kind of touched on this a little bit before, and the low pass filter 1 on the gyro and on the D term are dynamic by default, and they range from 150 to 450 or whatever you have your max set to. So it's essentially following the motor peak to some extent. When you have the dynamic notch range set to auto, this has to deal with how high the dynamic notch can move. There's different frequencies that the FFT samples. So you can see that the theoretical range gets higher with each of those. When your dynamic LPF gyro max is set below 333, this automatically in the auto setting will set the dynamic notch to work in the low range. If it's above 333 but below 610, it's in the medium, which is going to be almost all 5-inch quads. It would be a rare exception for that. And then micros, 3 inches, and whoops are going to automatically be set to high range, which is what they need to get that dynamic notch to go up to that 800 hertz. Again, setting this value is, if you're using black box, the OSD element is great for the quick and dirty, but it's not as tried and true as running a black box log. So if that's something in your wheelhouse, go ahead and do that on that flight. Pull out, do a spectrum of your traces, look at your peak. This is when I'm down at low end throttle, this is when I'm at 100% throttle. Find the max FFT or the max peak here, add 25 hertz to that, and that would be at the 510. And that's the setting you'd use here. To see what the dynamic notch is doing, if you want to get into that detail, so this is my people now, you would set your debug mode to one of two things. It's either gyro, the tried and true gyro scaled, which will show you the post-filtered noise, but if you want to kind of dig into the next level and say, okay, well, where is the dynamic notch tracking? What is the FFT center throughout the flight? If you set your debug mode to dynamic_LPF, you can see the raw gyro data on the roll axis. On the roll axis, you can see the notch center frequency. On the roll axis, you'll be able to see the low pass frequency cutoff. So that's that's throttle based. That is not following an FFT. And again, on the roll axis, you can see the pre-notch filter. So you'd see the data, the noise. This is totally raw, no filtering whatsoever. This is going to be after the low pass filters, but prior to the dynamic notch doing its thing. So it's kind of cool to be able to see, hey, what the raw is, what are the low pass filters doing, and then you can obviously just run a spectrum on the gyro traces themselves for the fully filtered data. Another option is the FFT frequency, and then here are the settings for that. It basically rolls in pitch, so you can see roll and pitch for the center frequencies, not just roll. From a tweaking out your tune standpoint, some things I would look at if I were you is really raising up this D-term low pass 2. So I would probably take this up to 230 and change it from bi-quad to PT1. Again, you have to go into the CLI for now for that, so you go into get low pass, and then you can see that D-term low pass 2 type is bi-quad by default. You could change that to PT1. And keeping in mind, it would not make these changes yet that I'm talking about right now until you flew the defaults. This really varies. If you have a low noise quad, these are some of the things I'm talking about. But if you do want to play around with it a little bit, that's the first thing I would do, is change it to PT1, bring that up. The other thing I would do is look at taking this to 2.2 or even higher, maybe even 3. You can see how that latency drops down here pretty good. So try 2.2. Or the other option is leaving this at 1.2 and then changing this to 0, and then that just goes back to a single notch. I kind of like better having the wider attenuation down here at the bottom and just bringing this up to 2.2. But give either a try, see what you like. At that point, you can see at 50% throttle, you should be at a 4.1 millisecond latency, 2 milliseconds on your D-term, and about 2 on your gyro. That's pretty good. Obviously, that gets lower. That gets into the 3s as you're getting up to 60-70% throttle. You can keep pushing that as much as your quad can take. Again, filters are just like porridge. You want enough, but not too much. Filters aren't a good thing. They're a necessary thing, but we want to try to reduce those as much as possible. So the defaults are a little conservative, and I know this regime of having our low pass filters go so high is kind of possibly new to everybody, but that's the benefit of all the improvements that have been made to the dynamic notch over the life here of Betaflight 4.0. It's carrying more of the load, it has a lower overall latency than low pass filters, so we need to be getting used to our low pass filters. You can see, at 50%, 70% throttle, this one's moving all the way up to 448 hertz. So it's moving up with the peak pretty good. And yeah, same thing here with the D-term. Now this only goes up to 200 hertz. If you are interested in exactly how the filters are moving up, you can kind of go to the end of the Excel sheet here, and you can see this is the gyro LPF and the D-term LPF right here, and you can look at that right here. So you can see on here at 150 hertz with the settings I have in there, that's why, you know, as your throttle goes down to 0, once it gets to 150 hertz right here, it kind of parks. So you can see it around 20% throttle, that low pass filter will just park at 150 hertz. So that's why that 150. So as you move that up, then that means it's going to kind of park itself at a higher setting, but that means that it will stay there until you get above 30% throttle, so on and so forth. Okay, well that is it. Hopefully that was helpful. Drop any questions, comments below. I'd love to hear your feedback on these new improvements. What do you think? How's it working for you? If it's better, great. If it's worse, try some of the adjusted settings and reducing your filtering down. And always you can turn stuff off and go back to a single notch that's dynamic. You can turn off the dynamic notch altogether, and you can set your dynamic low pass filters to be static low pass filters by setting those min variables to 0 and make that, you know, just the same as it used to be filtered in Betaflight 3.5 or 3.4 or 3.3. Thanks everybody, and I hope this helped.